In fact, in the last class we promised that we will show the viscous sublayer and the turbulent boundary layer. Okay. So, this is basically what you see, this is basically the inner region, and this is basically the global structure of the turbulent boundary layer. These are the large eddies, here the eddies are kind of small. This is a fully turbulent sublayer, and out of this, this is the laminar sublayer that we talked about. Okay. So, the formation of the viscous sublayer is the time average superposition of the laminar shear layers with local Reynolds number no greater than 100. So, locally in that particular sublayer, the Reynolds number values will not be more than 100. Okay. So, after this you have the fully turbulent sublayer where the eddies are small, right, and then you have the full turbulent outer region where the eddies are large, right, and this is of course the free stream velocities and the temperature. Okay. So, this is how this is the description of basically the total problem. Now, moving on to the heat transfer. Okay, we already so this is the heat transfer in turbulent boundary layer. Okay. So, we have already said that very close to the wall, remember we already started doing this. So, very close to the wall, alpha plus epsilon h dt by dy equal to minus q naught double prime rho Cp. Okay. So, this is the heat flux at the wall. Okay. This we have done by neglecting the convection effect, right, very close to the wall. This is what we said was the apparent heat flux, okay, apparent heat flux which is not a function of y, similar to our apparent shear stress assumption, right. So, once again we did the same thing. Okay. So, you define the non-dimensional quantities . Okay. So, after putting in all the variables, rho Cp u star divided by minus q naught double prime dy plus okay. So, that is the expression, or rho Cp u star dy plus okay. So, that is the form that you get. So, your T plus is T naught minus T bar, then there is a rho Cp u star divided by q naught double star. So, this particular factor, as we know, is a function of y plus, obviously, right, and this particular guy is a function of x plus, because u star is a function of x plus, right. Okay. And then you have the q naught, which is the wall heat flux. So, now therefore given as Cp u star divided by q naught double prime minus T bar. Okay. So, therefore, where this is called the turbulent Prandtl number, this is called the turbulent Prandtl number. Okay. So, as you can see, it is a combination, the profile, the way that we have written, it is a combination of the 1 over the Prandtl number, 1 over the turbulent Prandtl number, and the ratio of the eddy viscosity and the corresponding kinematic viscosity, right. Okay. So, this is a fully integrable form of the equation, okay, except that in fully turbulent region, epsilon m by gamma ky plus, right. So, that is your that is we already proved it from where, the Prandtl mixing length. Right. Now, if your Prandtl number and your turbulent Prandtl number both are of the order 1, okay, both are of the order 1, then epsilon m by gamma into 1 over Prandtl number T, right, this guy will be greater than 1 over Prandtl number if your y plus is large, right. If your y plus is large, this will be true, right. So, using this, okay, therefore, we get a 2-stage solution for our temperature. So, that 2-stage solution will be, so T plus from 0. So, this is what we call the conduction sub layer, the upper limit, okay, dy plus divided by 1 over Prandtl number plus some negligible terms, right. So, this is what we call the conduction sub layer, right, plus you have from the sub layer CSL all the way up to any y plus. So, this will be dy plus divided by some negligible terms, because the Prandtl number is now kind of low compared to this epsilon m by gamma. So, this is what we called the eddy transport layer. Got it? So, what we have done over here is that we have divided now the problem into 2 parts. Okay. The first part of the problem is basically we found out that one part was dependent on your Prandtl number, while the other part was dependent on your eddy viscosity, right. Okay. Using those 2 expressions, okay, we have been able to separate the 2. So, we are initially considering a conduction sub layer and then an eddy transport layer, knowing the fact that epsilon by gamma actually goes up, okay, with y prime, y plus. Okay. So, Now, the point is that okay, so these are the two layered information that we have. Okay. Now, of course, Prandtl's formula for delta x, right. So, now for delta by x, okay, what Prandtl assumed was ux u infinity x to the power of minus 1/5. If you recall, this is what we did for the overall boundary layer thickness. Okay, but this does not obey, we told earlier also, this does not obey the wall profile. Got it? This does not obey the wall profile, right. This was the original Prandtl's mixing length, Prandtl's formula for delta x, not mixing length. So, we redo this using the original expression for from the law of the wall, if you recall the logarithmic form. Okay, if you extend it to the edge of the boundary layer, to the edge of the outer region, let us see what we get. So, we can redo this whole thing, where you know that your u plus is a ln y plus b, right. So, your u infinity by u star, okay, that is where it becomes actually the same as so where your u bar becomes equal to u infinity at y basically equal to delta. You have a ln, okay, delta u star by gamma plus b, which gives you 1 over k ln delta u star by gamma plus b. Okay. So, this therefore leads to u star gamma plus b, right. So, we have this expression as your 1, you have rho Cp u star T naught minus T infinity by Q naught square. This is the other expression CSL plus Prandtl number T by K ln delta u star divided by gamma y plus CSL, right. So, this is your expression 2. Okay. So, these are the two equations that you get, okay, just by substituting. So, what we have done is basically you get the two temperature profiles, right. You get the two temperature, you get the two temperature profiles over here when you actually integrate, like if you look at it here, the conduction sub layer, the total temperature profile, right. But when we in order to find out what will be the velocity profile, we could have used Prandtl's form, but the problem here is this Prandtl's form does not obey the wall profile. So, you cannot take a temperature profile which obeys the law of the wall, right, and you take a velocity profile which does not obey the law of the wall. So, what we have done is in essence is that we have taken the temperature profile, we have taken the velocity profile, okay, and we have extended it to the outermost edge of the boundary layer, okay, to the outermost edge of the boundary layer to be consistent with this particular formulation, right. So, once we do this, so what we do, we start with the generic profile, then you substitute the parameters, that means u bar becomes equal to u infinity at y equal to delta, then you substitute it and at the end you get a profile which is essentially like this, right. Similarly, for the temperature part, if you set T equal to T bar equal to T infinity, okay, and y equal to delta, you get this particular expression from the total equation solution that we actually did, okay. So, these will be the two expressions. However, the temperature in itself, okay, if you write the temperature in two parts, the temperature in itself will be Prandtl number y plus, for y plus is less than y plus CSL, and it will be Prandtl number, okay, y plus CSL plus Prandtl number T by K, okay, ln y plus CSL, okay, when y plus is greater than y plus CSL, right. Okay. So, from, as you can see from this expression itself, okay, if you push it there, you can actually extract that that will be the total value, right, because this part is constant, right. Okay, and if you substitute your y plus, okay, by substituting y equal to delta, you basically get that, right. So, in other words, and we already know that T plus, we defined T plus right here. Right here, okay. So, that was our T plus, okay. Only difference is that T plus evaluated at y equal to delta means that T bar should be equal to T infinity, right. That is the only change that you will have, okay. So, it is basically that, it is T naught minus T infinity, then you divide it by Q naught square, and then you have this, and then you have on the right hand side you have the full expression, okay. So, similarly the same thing we have done it for velocity. Remember, this is not Prandtl's assumption, assumed velocity profile, because remember that does not follow the law of the velocity profile, got it, okay. So, these are the only two changes that we have made, okay. Now, if you look at these two expressions clearly, okay, what you will find is that from these expressions we can eliminate a few things, okay. We can eliminate a few things, and basically what we need to eliminate. So, let us write eliminate delta u star by gamma, okay. If you eliminate these two expression from equations 1 and 2, we get u infinity by u star, okay, is equal to 2 by CFX raised to the power of half. That is what you get. Keeping in mind, okay. So, we eliminate this, sorry, this is not we get, and this is the definition of u infinity by u star. So, using these two expressions, the total result becomes h by rho Cp into u infinity. This is a long expression, a half CFX divided by Prandtl number T plus half CFX raised to the power of half. Okay. So, what we have done, let us just recap very quickly. So, we have two expressions 1 and 2, right, which are basically the wall laws which are applied at the edge of the boundary layer. Okay. So, equations 1 and 2 are wall laws, right, applied to edge of boundary layer. Edge of boundary layer, which is basically your delta, right. So, you, and we also have the definition of CFX which we got earlier. So, what we do is that we eliminate this from equations 1 and equation 2 and apply this definition, so that we get the new quantity which is given as this. Okay. Now, this particular number that you see over here is dimensionless. Okay. So, this is actually a dimensionless number and it has got a name, it is called the Stanton number. Okay. It is called the Stanton number. Okay. So, it is one of the dimensionless way of reporting the heat transfer coefficient in turbulent flows. So, Stanton number basically if you write it in terms of x, it is a rho Cp into u infinity. It is basically a Nusselt number divided by the Peckley number, right, or in other words it can be Nusselt number divided by Reynolds number into Prandtl number. Okay. That is what Stanton number is. Okay. So, now if you look at, let us call this equation 3. Now, if you look at this equation, what we get is that your Stanton number is therefore given as half over Cfx. I am writing it a little large so that you have no problem in understanding. Okay. Now, before I write the denominator, okay, what we can do is that people have found out these empirical constants. There are quite a few of these empirical constants which are lying around here. So, finding those empirical constants, okay, people have plugged in some numbers. Okay. So, for example, it becomes 0.9, that is the turbulent Prandtl number is 0.9, this Cfx raised to the power of half. So, as you can see 13.2 into Prandtl number minus 10.25. So, you can see your y plus CSL is approximately 13.2, right, is approximately 13.2, and B, this constant B over here has been, usually it is found out to be about 5.5, something of that order. Okay. And Prandtl number is assumed to be in the range of 0.5 to about 5. So, it is of the order 1 essentially, and Prandtl number, turbulent Prandtl number is also of the order 1, it is about 0.9. Okay. So, that is the expression that we get. So, as you can see, if you look at it very closely, this entire expression, the Stanton number expression, you find that it is not very sensitive to the changes in Reynolds number, particularly the denominator part. Okay. It is dependent only on the Prandtl number, so to say. Okay. It is only dependent on the Prandtl number and it has got the same order of magnitude and the factor as the Prandtl number over here. Okay. So, that so indeed, so if you do it like that, so all are of the order 1 actually. So, therefore, if it is, since it is dependent only on Prandtl number, so Prandtl number 2/3, if you just take all the things out, okay, 2/3 is equal to half Cfx. This is the expression that you get after simplification. Okay, after simplification. Okay. So, this particular expression that you see over here is originally was suggested by Colburn. Okay. So, it was suggested by Colburn. Okay. And this is an interesting quantity in the sense that we are relating the skin friction coefficient with the heat transfer coefficient using this particular relationship. Okay. So, there is an analogy basically that happens between the two. Okay. It is valid for a range of Prandtl number basically less than 60 and greater than about 0.6. Okay. So, of the order 1 to 10, it is kind of valid. Okay. And this happens only because this is not very sensitive, the denominator of this particular expression is not very sensitive to the change in Reynolds number. Why? That is because if you recall your Cfx variation with Reynolds number, it was rather poor, right. It was Reynolds number to the power of minus 1/5, right. So, even if your Reynolds number changes quite a bit, your Cfx changes just by a little bit. Okay. if your Reynolds number changes quite a bit, your CFX just changes just by a small bit. So, that is why this denominator is largely insensitive to your Reynolds number variation, but it is sensitive to the Prandtl number variation. Okay. So, because it is sensitive to the Prandtl number variation, that this skin friction coefficient and this Stanton number are basically proportional to each other. They are of the same order of magnitude, with the only function being the Prandtl number, which fills in as a constant of this proportionality. Okay. That is exactly what we have seen over here, that this is the expression which will come in very handy, that Stanton number into Prandtl number 2/3 is basically equal to half of the skin friction coefficient. Okay. So, this completes a nice little thing. So, we know that the temperature also has got a laminar sublayer and then a fully turbulent sublayer. Okay. At the same time, we found out that there is an analogy between the heat transfer and the skin friction coefficient for Prandtl number, turbulent Prandtl number of around 1 and Prandtl number to the order of also varying in that range 0.5 to about 50. It actually agrees. So, in the next class what we are going to do, we are also going to see that how this same relationship can be worked out, okay, in a slightly different way, okay, and we will see to that how that particular thing can be incorporated in this particular analysis of ours. Thank you.